Hello everyone, my name is Juan Fraire, and in this opportunity we're going to present our talk entitled From Space to Underwater Networks. We are going to present this talk together with Tobias Nöthlich, my colleague from D3TN in Germany, and the projects and context we're going to present here are different challenges and opportunities we have faced together with our company D3TN, which is a company based in Germany, Dresden, and also with offices in Miami. And we cover mostly topics about challenger networks, comprising context from space, offshore, underwater, vehicular, and remote regions connectivity. So, as mentioned, D3TN is a company that is based in Dresden. The headquarters are located in this beautiful city in Germany. We also have offices in Miami, and we specialize mostly in networkings and data infrastructures for challenging environments, which include vehicular, underwater, and space. The company competencies revolves around consultancy on network architectures and management. We do also simulation, emulation, and experimental analysis around networks applied to this challenging context. We also develop and maintain our own protocol stack, term coined micro D3TN, which is a delay-tolerant networking protocol stack developed for space, but also challenger terrestrial networks. And we also take care of the deployment of data infrastructures for such challenger environments. We do have several projects with different partners, mostly with ESA, the European Space Agency. We also have collaborations with NASA in the US, and we also are supported by different entities from Germany, including the Federal Ministry of Education and Research, among other German institutions. Further information about the company can be observed in the d3tn.com website. And in this presentation, I'm going to introduce you which are the main technological solutions D3TN offers, and I'm going to dive into the details of the projects that push the company to develop these novel technologies for space networks and beyond. So the main motivation of D3TN is to cover and provide solutions for a variety of diverse networking segments. Of course, we start from the internet on the left-hand side in this image, where the company has expertise in deploying the infrastructures, computational infrastructures, data lakes, warehouses, and also infrastructure for data centers and general computation infrastructures. We also explore networking solutions for space systems, including nanosatellites, but also deep space, not only near Earth orbit, where communications can be challenged by delay or disruptions in the communication links. These delays and disruptions help us and allows us to also provide solutions for contexts like offshore and also vehicular systems, where the movement and the sporadic connectivity from vehicles also provokes similar effects on the networking characteristic than those seen in space. The same effect is also observed in other contexts where underwater sensor networks also experience high delay and high latency that needs to be tackled by means of delay-tolerant networking technologies. So as a result, delay-tolerant networking protocols, specifically our micro D3TN protocol stack I mentioned, is a perfect protocol stack solution for covering all these networking segments from the internet, bridging it to space systems, offshore wind parks, vehicular systems, underwater sensor networks, and furthermore. Again, the main technological value here is to incorporate delay-tolerant networking protocols that allows us to keep data stored arbitrary amount of time and intermediate nodes, but also not assume immediate responses from the end node as it is assumed in most of the internet protocol solutions. How is this achieved? This is done thanks to micro D3TN. Micro D3TN is our delay-tolerant networking protocol implementation. It is a lightweight solution. It was originally thought for running in microcontrollers, so therefore micro D3TN shows a very low memory footprint and reduced dependencies. And as I said, it can run on very reduced resources, but also including POSIX and Linux interfaces. Micro D3TN was the first space-based BPv7 protocol stack I'm going to mention in the mission where this was tested. And it is offered as an open source solution under a BSD and Apache license that is accessible via our public repositories. And as I will mention in the next slide as well, we offer an enterprise professional edition where extended features and support can be provided. Micro D3TN offers an upper layer of known as application agent protocols, which is an interface where end users' applications can be plugged in. This plugin is offered by means of a northbound interface implemented by a socket-based interface that allows access to the core of the application where multiple delay-tolerant networking features, including neighbor discovery and bundle encapsulations, can be used. On the southbound interface, convergence layers adapters allows our micro D3TN protocol stack to plug into classical convergence layer adapters using classical internet protocols, but also CCSDS and space-specific protocols. About three projects that allowed us to develop this technology, I'm going to talk about this in the next few slides. The first project one of the first that we tackled early in 2019 was the Colsan project funded by the European Space Agency. And in this project, what we managed to do is to connect underwater sensor networks by means of acoustical modems that send data by means of underwater acoustic waves to a buoy that was gathering and collecting this data from the multiple nodes, collecting this data, storing this data into a micro D3TN implementation stack running on the buoy itself, and relaying this data to passing by low Earth orbit satellites, which is a service that was offered by Orbcom. And the data was stored in this intermediate buoy until the satellite was visible on site. The satellites relay the data by means of this space orbital network to the ground segment where our D3TN database, visualizers, and toolchains was actually running on. And therefore, by means of using bundle protocol, which is the protocol implementing delay-tolerant networking principles, allowed us to send data in a completely autonomous manner from underwater networks down to our own premises in the cloud hosted on the internet. Further projects on 2022 extended these concepts to also optical modems from Hydromea. It's a company that builds optical communication system for underwater, where we were able to integrate our micro D3TN with the modem built by this company, also bridging data transport from underwater to underwater systems. A second key project from the company was our flight testing on the OPS-SAT satellite from the European Space Agency. This experience allowed us to flight test in orbit micro D3TN, and in this opportunity, the bundle protocol version 7 was deployed in ESA's OPS-SAT, which is the nanosatellite we see in this image. And in collaboration with Spatiam, we were able to also include an ION protocol stack, which is the green rectangle we see on the right-hand side, where this is a NASA implementation of the DTN protocol. And we also validated interoperability features between micro D3TN and ION. The key use case for this project was to connect remote users by means of classical HTTP gateways, encapsulating that data into bundle protocol payloads, forwarding this data to the passing by satellite via ESA's gateways and control ground station. The satellite would relay this data back to ground to another ground station gateway that allowed the data stored on board to be delivered to what we called as hotspot, in contrast with a cold spot, which is an isolated node. A hotspot is connected to the internet and hosting another micro D3TM protocol instance. The payload was able to be recovered and delivered to a web server on the internet where this data was processed, and a response was sent back to the cold spot node by means, again, of the OPS satellite, therefore using delay-tolerant networking protocols, leveraging store, carry, and forward techniques, namely no immediate expectation of the end node responses, or tolerance to delay on the intermediate links, such as the delays we had with the OPS sat, because of course this is a low Earth orbit satellite, and the visibility to the satellite was essentially limited to a few minutes per day. But the protocol handled this in a fully autonomous manner, and data was sent and received from the cold spot to the hotspot node in a fully autonomous manner. The second project that followed OPS-SAT was the Red Mars project, funded by the Federal Ministry of Education and Research in Germany. And the Red Mars project ran in 2023, and the core approach of this project was to leverage existing recursive internetworking architectures, also known as RINA, where the idea of using different scopes of networks was leveraged to interconnect different regions of delay-tolerant networks, in this case emulating what could be an interplanetary network, where users on the ground are able to connect to satellites on the solar system scale, and these satellites in turn are able to send and deliver data to remote drones on potentially operating on the Mars surface, which is the scope number 3 in the yellow region shown on the image on screen, and therefore leveraging the bundle-in-bundle encapsulation, or BIVE feature from the bundle protocol specification, where different scopes can be bridged together and operated in an autonomous manner, but still ensuring interoperability and data transport between these different regions that can be potentially operated by different entities all together. This is mainly making a use case here where, for instance, some space agencies can operate the regions in yellow, so for instance, scope number 3. Another space agency can control scope number 2 in green on the left-hand side, and then scope number 1 is a higher layer scope that is bridging scope 2 and 3, and allowing an exchange of data using this bundle-in-bundle encapsulation feature that allows us to hide the details of the underlay transport to other scopes. This project successfully demonstrated that this type of layering techniques can be applied in delay-tolerant networks, and therefore facilitating and enabling sophisticated operations across very large systems like the solar system internet that can, in order to be operated by multiple actors, still holding a significant interoperability opportunity here. The same interoperability features were exposed in the IceCube project. Also, was hosted on the same year. The IceCube project was a collaboration project between ESA and NASA with D3TN as a company. And the core idea of this project was to profit from the IceCube nano satellite that was launched on the moon by the Artemis project. Unfortunately, the IceCube satellite was not able to bootstrap properly after the launch due to some issues, but still all the infrastructure that was laid out to transport data from the satellite to ground across NASA, ESA, and D3TM, playing the role of an external company user, was still used to validate the concept altogether. So what happens in this project was that the data that was downloaded by the satellite, or in the emulation setup that was finally executed due to the issues I mentioned, the data was collected by ESA ground station in Kourou, or by NASA ground stations on JPL, And this data was successfully exchanged in a fully autonomous manner over TCP/IP bridges and TCP/IP firewalls, and delivered to demilitarized zones from ESA and accessed by D3TN as a company by means of TCP/IP WebSockets. And thanks to the delay-tolerant networking protocol that was implemented end-to-end, so this namely this means from satellite itself to JPL at NASA to ESA and also to the WebSocket interface that was implemented by D3TN, this data handling and data transport was achieved successfully in a fully autonomous manner again. If no DTN protocols could have been used here, very sophisticated and cumbersome VPN configurations would have to be taken place because of these interoperability features that we are going to exploit by using micro D3TN on the D3TN side. NASA JPL was using ION and ESA was using DTN application from ESA. We were able to transport the data efficiently without any major hiccups and demonstrate that the DTN protocol stack is also a very appealing solution for cross-connecting and interconnecting different space agencies in different domains. Another project that we also took forward this 2023 was D3TN ES. D3TN Enterprise Stack, or ES, is actually the evolution of the micro D3TN stack that is open source, but bridging these to more sophisticated features that are actually needed in commercial deployments, including interoperability, maintenance, and support. D3TN ES specifically includes solutions like generic bundle forwarding interface, which is a means to control and execute a fine-grained control of how bundles or packets in terms of detailed delay-tolerant networking protocols can be actually controlled using external algorithms and external routines fitting specific solutions and specific needs for the customer. This feature is not available in our open source edition and can be obtained by means of the D3TN ES version I'm mentioning here. Also, D3TN ES includes a forwarding information base that allows sophisticated multi-hop routing and caching techniques to be also executed by the enterprise edition of our D3TN protocol stack. Most recently, the project that motivated us quite intensively was the Solar System Internet Pre-Phase A project, where there was a tender from the European Space Agency, or ESA, where GMB, Novaspace, and us, D3TN, collaborated in a consortium to provide support in the pre-phase A of the Solar System Internet project. This program, now known as SSI Pathfinder, was actually nourished by multiple analyses we executed together in this consortium in order to provide a network-centric interplanetary network, including the analysis of radio frequency, optical data relays, lunar DTN node specification, and high data rate Earth observation downlinks analysis. Finally, the project that is keeping us busy in these days, and we are going to share a few more details with you, is the Dark Sol project, where we aim to specify and design space cloud architectures. And for this, I'm going to hand over to Tobias, who is much more knowledgeable than I on the Dark Sol project, to provide us further details and show us what's behind this space cloud architecture idea in Dark Sol. So I appreciate your time. Thank you for listening. And now I pass the talking to Tobias.
Thank you, Juan. Now, before talking about what the Dark Sol project is about and how we're tackling it, let's also briefly dive into why we're even doing this. Now, the reason is that in traditional space missions, there is a reliance on dedicated hardware running single-use application, which leads to inefficiencies, excessive costs, and also unnecessary environmental impacts. Now, one such impact is the creation of space debris, either through rocket launches or through the incorrect deorbiting of inactive satellites, which, well, themselves could also be hit by space debris, causing them to fall apart and creating even more debris objects. Now, there are some numbers on the slides provided by ESA, which shows that they are tracking over 50,000 space debris objects with a size of over 10 centimeters, which, as a sort of analogy, is roughly the size of a grapefruit. They have track over 1.2 million space debris objects with a size of 1 centimeter to 10 centimeters, and over 130 million space debris objects with a size of 1 millimeter to 1 centimeter. Now, to mitigate the problem of space debris, we need to obviously mitigate the creation of space debris, which could also be done by reducing the number of rocket launches. This is obviously not that easy because every rocket launches a new mission, which gathers data or, well, does processing in space, and there's no way to have a follow-up mission without a new satellite. Now, this is where cloud technology could come in, because cloud technology enables quite a few benefits which would also be nice to have in space. Among others, it enables ubiquitous access to services and data, it provides scalable and flexible computing resources, it supports high availability and fault tolerance, something that is also quite important in space, facilitates rapid deployment and updates, which would potentially mitigate the number of rocket launches needed, and it is also very cost effective for many businesses because they would not need to launch their own satellites, they could just rent space on an existing satellite. However, it's not as easy because it was obviously not conceptualized for use in space, but for use on Earth. So it assumes low latency connectivity, which is also continuous, which is something we, well, don't have often in space. So we often face large latencies and disruptions, which is not something current cloud technology can deal with. Another point is that there is no standardized execution environment for space agencies, which limits adoption, and there is only insufficient tenant separation on space hardware software platforms, which means that if we have two companies executing their workloads on a satellite, there is a risk that company A can read the data of company B, which is something we do not want. Now, in space networking in general, there are two challenges. First of all, the disruptions. So if a satellite, orbits around the planet, then there are going to be periods of time where it does not have connection to any ground station, and delays. For example, if we want to send a message to Mars, in the worst case, it is going to take 20 minutes from when the message was sent on Earth to when it arrives on Mars. Luckily, this problem is fundamentally solved. There is a technology called delay and disruption tolerant networking which can deal with these disruptions and delays. However, the main question of whether it is possible to use cloud-native execution environments in space still remains. And this is what we're going to tackle with the DARKSO project. We found two partners, the University of Dresden and the Cyrus Technology GmbH, with which we want to address or find out whether there is a possibility to have DTN architectures for space cloud operations and space cloud lifecycle management. We split this overarching topic into three main research areas, which are each tackled by one partner. So TU Dresden will deal with delay and disruption tolerant cloud infrastructure, Cyberus will tackle a secure separation layer for multi-tenant operation, and we will look into this delay and disruption tolerant application operation. Now, a bit more detail. First of all, we're going to need a delay tolerant infrastructure to deploy our software to. This means that the research focus for the TU Dresden is going to be on models and architectures for workload execution in delay and disruption tolerant networks, with the goal of creating a robust infrastructure capable of operating efficiently in space environments with unreliable communication links. This also extends to other environments where we may have unreliable communication links, of course. For this, there's going to be quite a bit of research activities, quite a lot of analysis. So they need to do a requirements analysis for an execution environment. They need to look at the state of the art and analyze whether they could be used for space deployment. They need to build a concept and an architecture, form it into a prototype, and then scientifically evaluate this prototype. On Cyberus front, we will see the development of secure multi-tenancy, which means their research focus is for isolating multiple tenants on a single satellite, with the goal of developing a robust separation layer to ensure strict isolation between applications on this same satellite. For this, they will need to conceptualize a secure separation layer under laboratory conditions, research some test automation strategies, build a test bed where they can also do fault injection and hardening of the separation layer. They need to minimize it, and they also need to build a secure and fault tolerance update mechanism. Now, for MicroDTN, we are focusing on mechanisms for running cloud-native applications in space, with the goal of enabling seamless integration with delay and disruption-tolerant networks. A lot of analysis here as well. We need to select and analyze exemplary applications, do a detailed problem analysis in delay and disruption-tolerant contexts to find out which issues could be which issues could arise if we want to deploy applications there. Then we need to develop a concept to address these identified issues, build a prototype based on this concept, and test it using focused experimental setups. For this, we have 2 years. So the project started last year in October, and it runs until October 2026. It started with an analysis phase, which went on until April this year. We're currently in the architecture phase, which is followed by a system draft phase and the evaluation phase. Now, this is laid out sequentially here, but we are following an iterative approach, which means that if we, for some reason, find new challenges or requirements in a later phase, we can also revisit previous phases to address these challenges or new requirements. Now, the current status on the architecture is as follows. There is an image here which, well, depicts the space cloud. And the space cloud consists of individual clusters that can exchange information via non-persistent, even potentially episodic links, which are quite high latency. So we're talking about latencies in the range from milliseconds up to minutes. As mentioned, to Mars, one-way connection could be 20 minutes. Each cluster contains at least one and usually multiple nodes. These nodes can be anything from satellites to space probes or robots, if we're talking about space. And they can also be obviously computers or satellite phones on Earth. Main requirement is that they are running the dark soul execution environment, the space cloud execution environment. And also they need to be connected to the other nodes in the cluster in a low latency persistent connection. Each cluster must have at least one node responsible for managing the cluster. This could be multiple nodes as well, and these nodes may also simultaneously execute space cloud workloads. Now, as mentioned, a cluster may include nodes both on Earth and in space, provided there exists a persistent low latency connection between them. This is pictured, for example, in cluster 5. We can have nodes on other celestial bodies, such as the Moon, for example, may also be included in cluster 3. A cluster located in Earth's orbit, for example, can also connect to a ground station through a non-persistent high latency, but in this case then periodic link. This is depicted in cluster 2. Now, obviously, the ground station is not going to be considered part of the cluster because there is no low latency connection, low latency persistent connection to the other nodes of the cluster. The same goes for data relays, which could be used by, for example, clusters in deep space to transmit data back to Earth. They don't have a low latency connection, and they also do not run or not necessarily run the space cloud execution environment. Now, the last type of cluster are isolated clusters, so clusters that may also operate in isolation after initial setup, which do not have any direct connections to other clusters. These clusters would then remain disconnected from the space cloud for an indefinite period of time, still executing their workloads autonomously. Now, after talking about what we built so far, what the goals are, let's also talk about what impacts Dark Soul may have. There are quite a few benefits we could achieve through bringing cloud technologies to space. For example, we may reduce costs and risks for satellite robotics and space probe missions because we no longer, or well, potential users no longer need to send their own probes, their own robots up in space. They could just use robots or satellites which are already part of the space cloud. We can decrease dependency on proprietary or terrestrial focused solutions because we're planning on making this open source. We can facilitate the development of space-specific applications and services. Once again, you do not need to launch your own satellite to verify your software in space. You could also just use, well, a Dark Soul node. We promote efficient resource utilization, also potentially reduce space debris because there's going to be less rocket launches because we, well, need to send less satellites up in space. This could contribute to the development of an independent space technology ecosystem and also provides valuable feedback to state-of-the-art cloud-native technology projects about their applicability to challenged environments. Now, this concludes our short overview of what we're doing at D3TN and what we're working on in the context of the Dark Soul project. Thank you very much for your attention.